pumps come in many shapes, colours and sizes, but they will typically look something like these. These pumps are inline centrifugal type pumps, which means their inlet and outlet are aligned, and the method of moving water is via centrifugal forces. We're going to find these pumps used to circulate hot water around a heated water circuit. That way, when we open a tap, we almost instantly have access to hot water. Otherwise, every time we open a tap, we would have to wait for hot water to flow through the entire system. In hydronic heating systems, we will also find these pumps used to circulate heated water between the boiler and radiators or other type of heat exchangers. We might also find circulating pumps used in larger heating systems to supply heat to different parts or zones within a building. The circulating pump consists of two main parts, the pump and the motor. The motor is an induction type motor, which allows us to convert electrical energy into mechanical energy. This mechanical energy is used to drive the pump and move the water. When we look at the pump casing, we have an inlet as well as an outlet. The pump pulls water in through the inlet and pushes it out through the outlet. Typically, there will be an arrow on the casing to identify the direction of flow, so you know which is the inlet and which is the outlet. As this is an inline pump, the inlet and the outlet are aligned concentrically. This is useful because we could potentially cut a section of pipe out from a hot water system and install a circulating pump within this space. And we could do that without having to alter the pipe work like we would have to with a standard centrifugal type pump. This is still a centrifugal type pump though, so the water needs to enter the pump via the eye of the impeller. To achieve that, the inlet follows this curved path which sweeps around into the impeller. This part is the pump casing. It has a channel inside known as the volute. After the water exits the impeller, it will collect in this channel and make its way to the outlet. We're going to see that in more detail a little later in this video. Next, we find the impeller. This sits within the pump casing and is surrounded by the volute channel. The impeller rotates and imparts a centrifugal force on the water which pushes it out of the pump and through the pipes. Behind the impeller, we have the backplate. The backplate acts as a barrier and keeps the flow of water within the pump case. The backplate also holds one of the bearings for the shaft to ensure a smooth rotation. Attached to this, we also find a rubber seal to prevent leaks. Next, we're going to find the shaft and the rotor. The rotor is attached to the shaft, and the shaft is attached to the impeller. When the rotor rotates, so will the shaft and the impeller. That's the driving force of the water within the pump. The rotor sits within the rotor can. The rotor can provides a physical barrier which prevents any water from coming into contact with the electrical circuit of the induction motor. Surrounding the rotor can, we have the induction motor. This consists of a number of coils of copper wire which are tightly packed into the stator. The coils as well as the stator are stationary and do not rotate. Electricity flows through the coils within the stator. This will create a rotating electromagnetic field which causes the rotor to rotate. Protecting the stator and the coils, we have the motor housing. On the side of the motor housing, we will find the electrical terminal box. On the front of this, we find the speed selector switch. This allows us to manually change the rotational speed of the motor between low, medium and high. This changes the flow rate of the pump. Inside the terminal box, we have the speed selector switch. We also have the ground, neutral and line terminals, which allow us to connect the pump to our power supply. There is usually also a capacitor inside this type of pump. The capacitor is vital to the operation of the pump, so we're going to look at this in detail just shortly. The electrical motor within the circulating pump is a single-phase alternating current induction motor. Electricity is the flow of electrons through a wire. We have DC or direct current which we get from supplies such as batteries. And in this type of electricity, the electrons flow in just one direction, from the negative terminal to the positive terminal. However, the electrical supplies in your homes and places of work will be a different type of electricity known as alternating current. With alternating current, the electrons alternate in direction and flow forwards and backwards repeatedly. As electricity flows through a wire, it generates an electromagnetic field. When the electrons change direction, the magnetic field continuously expands and contracts. By wrapping the wire into a coil, we generate a much stronger electromagnetic field. When a wire is wrapped into a coil, we call this an inductor. When we apply an alternating current to the inductor, the magnetic field expands and collapses, and each time it expands and collapses, the north and south polarity of the coil reverses. We need this expanding and collapsing magnetic field to create rotation. To form the motor, we wrap the wire into two coils within the stator to create a large electromagnetic field. If we place the rotor in the center of this magnetic field, the rotor will align with the magnetic field and then it becomes stuck. To spin the rotor, we need a rotating magnetic field. If we took some magnets and carefully timed them to interact with the rotor, we could achieve this, but it's not very practical. In larger motors, we create the rotating magnetic field by using more phases. This is because the electrons flow forwards and backwards at different times in the different phases. This will therefore create another magnetic field at a different time. However, the circulating pump we're looking at only has a single phase connection, so we will instead use a capacitor to create a fake second phase. We therefore insert a second coil into the stator, which is 90 degrees rotation from the first coil. The two coils are wired in parallel, but the second coil has a capacitor connected in series with the coil. Electricity doesn't pass through capacitors. The circuit is broken inside a capacitor to form two walls. Therefore, the capacitor is something like a storage tank or a diaphragm. When the supply of electricity moves in one direction, the capacitor will store electrons. When the electricity supply reverses direction, the capacitor will release electrons. This way, we have electrons flowing through different coils at different times. This will create a rotating magnetic field. The capacitor has to be sized correctly to achieve this though. We have covered the basics of capacitors in detail in a previous video. Do check that out, links down below. Typically, we have a switch on the side of the motor terminal which allows us to change the speed of the motor and thus the pump flow rate as well as the head pressure. Inside the motor, the run coil will have various connection points, or there might even be a number of different coils. The switch is used to connect onto these different points and effectively change the length of the coil which electricity needs to pass through. Now I know some of you will be wondering, why does the low setting have a longer coil than the high setting? When we pass an alternating current through an inductor, the magnetic field it generates interferes with the electrons trying to pass through it. A force known as inductive reactance opposes the change in current. When we increase the length of the coil, the inductive reactance also increases, and this makes it harder for the current of electrons to flow through. As the current has therefore reduced, the electromagnetic field also reduces. This reduces the speed and torque of the motor. As we move to the lowest setting, the inductive reactance is at its maximum. The current is reduced and the rotor rotates slowly. When we move to the high setting, the inductive reactance is at its minimum, so the current is high and the rotor rotates much faster. We have covered multi-speed pumps and how to read their pump charts in our previous video. Do check that out, links in the video description down below. So, how does the circulating pump work? First of all, water enters the pump via the inlet and enters the eye of the impeller. The water will be trapped between the blades of the impeller within the pump housing. Electricity enters the terminal box and flows through the motor windings. The capacitor helps create a rotating magnetic field, and this rotating magnetic field forces the rotor to spin. Attached to the rotor is the shaft. The shaft runs from the motor and down into the pump housing where it connects onto the impeller. As the rotor rotates, so does the shaft and the impeller. As the impeller rotates, it imparts kinetic energy or velocity onto the water, and this moves outwards. By the time the water reaches the edge of the impeller, it has reached a very high velocity. This high-speed water flows off the impeller and into the volute, where it hits the wall of the pump casing. This impact converts the velocity into potential energy or pressure. As the water moves outwards and off the impeller, it's going to create a region of low pressure at the center, which pulls more water in, and so a flow develops. The volute channel has an expanding diameter as it spirals around the circumference of the pump casing. As this increases, the velocity of the water will decrease. This results in the pressure increasing. The expanding channel therefore allows more water to keep joining and converting into pressure. So, the discharge outlet is therefore a higher pressure than the suction inlet. The high pressure at the outlet allows us to force water to circulate